Ever look at your smartwatch, your coffee maker, or even your car and just wonder how it all works? Today on The Explainer, we are prying open the hood on those tiny, brilliant computers that pretty much run our world.
I mean, think about it. Your watch is tracking your heart rate, getting your texts, and updating the time, all at once, without skipping a beat. It feels like magic, doesn't it? But it's not magic. It's just really, really clever engineering, built around a very specific kind of computer system.
These are all called embedded systems. Now, unlike your laptop that can browse the web, edit video, and do a million other things, an embedded system has one job, and it's designed to do that job perfectly. At the very heart of that system is a special kind of brain.
So, let's start at the bottom, with the hardware itself. We're talking about the microcontroller. And no, this is not the same kind of beast you have in your gaming PC. It's something else entirely, something far more focused.
Think about your laptop's brain. Its CPU. It's a powerhouse for sure, but it's also needy. It requires a whole team of other chips just to function. Separate memories, separate storage, you name it. A microcontroller, or MCU, is the complete opposite. It's an entire computer system. CPU, memory, and all its little helpers squished onto one tiny, efficient piece of silicon.
And this all-in-one approach is what makes it so perfect for the job. If you look at a popular chip like an STM32, you see everything it needs is baked right in. You've got the processor core, you've got memory for its code and data, and you have all this specialized hardware called peripherals to handle communications, timing, even a unique serial number burned in at the factory. Okay, so we have this powerful, self-contained brain. But that just brings up the next obvious question, right? How does this one brain juggle all those tasks, monitoring your heart rate, displaying a notification, without just crashing? It needs a conductor for its internal orchestra.
And that conductor is the software. But we're not talking about Windows or Mac OS here. In the embedded world, the boss is something called a real-time operating system, or RTOS for short.
The most important word in that whole definition is predictable, and RTOS is obsessed with time. It's not just about being fast, it's about guaranteeing that the most critical jobs happen exactly when they're supposed to, down to the microsecond, and it has a very specific rulebook for making that happen.
Let's take a really popular one, FreeRTOS. Its core principle is a fixed priority preemptive scheduler. Sounds complicated, but the rule is dead simple. The highest priority task that's ready to run gets to run, period. And if a more important task suddenly needs the processor, it just cuts in line. It preempts whatever else was happening.
And what are these tasks it's managing? You might imagine some incredibly complex code, but a lot of the time, they're not. As the official documentation points out, they're often just tiny, simple, infinite loops, each doing one thing over and over again. Check a sensor, blink a light, wait for a button press. The trick is managing all those loops so they play nicely together.
So how do you stop all these tasks from tripping over each other? Well, the RTOS gives them tools, like traffic signals for code. For example, a semaphore is like a simple flag. One task can raise it to signal to another, hey, that thing you were waiting for, it happened. A mutex, on the other hand, is more like a key to a room. Only one task can hold the key at a time, so it can use a shared resource, like a communication port, without anyone else barging in.
All right, let's just take a breath here. A microcontroller with dozens of settings, a real-time operating system with tasks and mutexes. This sounds like an absolute nightmare to set up from scratch. How does anyone actually build a real product with all this complexity? Well, the good news is they don't have to start from zero. Developers have an entire workshop of amazing tools that automate the hardest, most tedious parts of the job, so they can focus on what makes their product unique.
The first tool in this workshop is something called STM32CubeMX. You can think of it as the project's architect. It's a graphical program that lets you visually plan out everything your microcontroller needs to do, and then it does all the grunt work for you. Honestly, the workflow is kind of magical. You pick your chip from a list, you click on pins and say you're for communication, you're for an LED, you check a box to enable FreeRTOS, then you hit one button and poof, it spits out a fully configured working C code project. All the boring setup is just done.
The code it generates uses something called a hardware abstraction layer, or HAL. And this is a total
game changer. It basically gives you a set of simple, human-readable commands to control the hardware. This makes development so much easier, and as the experts note, it means your code can be easily moved to a different, newer chip without a total rewrite.
So now we have our hardware, our RTOS conductor, and this amazing toolkit. But this creates a totally new problem. The system is running, but it's a black box. With tasks switching thousands of times a second, how in the world can a developer see what's actually going on in there? For that, you need the final tool in the workshop. You need something that can perform a checkup, something that acts like a real-time MRI for your running code, letting you see its very soul.
And that tool exists. It's called Seger System View, and it is, no exaggeration, a kind of MRI for your application. It hooks into the microcontroller and streams out data, giving you an exact, microsecond by microsecond visualization of what the RTOS and your tasks are doing.
Suddenly, debugging isn't guesswork anymore. You're not just staring at code for hours. You can see which task is running. You can see why the scheduler switched from one task to another. You can see hardware interrupts fire, watch your CPU load go up and down. You can even see tasks waiting for those mutex keys we talked about. The black box becomes a glass box.
And it's so flexible. You can run it in continuous mode to get a live feed like you're monitoring a patient's vitals. You can set it to single shot to capture one specific hard-to-catch bug. Or, and this is my favorite, you can use post-mortem mode. The system records continuously in a loop, so when it finally crashes, you can stop it and see exactly what happened in the moments leading up to the failure.
And what kind of difference can this visibility make? Get this. In one case, a developer used System View and found their CPU load was over 100%. Yeah, you heard me right. The chip was so overwhelmed by incoming data, it was literally drowning and couldn't keep up. But after seeing that, they realized they could offload the work to a special piece of hardware called a DMA. The result? The CPU load dropped from over 100% to just 10%. That's an optimization you would never find just by reading the code.
So, after diving this deep, what's the big takeaway? What really makes all our smart devices tick?
It's not just one thing. It's a hidden symphony. You have the incredible efficiency of the microcontroller silicon, the precise clockwork rhythm of the real-time operating system, and the incredible power of the developer's toolkit that brings it all together. This symphony is the invisible engine that enables our smart world, and it really makes you wonder, doesn't it? As this symphony of tools gets even more powerful and easier to use, what are they going to build next?